Like the Thinking with Typography book, just with an S?
Exactly like that, yeah, but not
Okay.
about print,
Not about
more about type
typography.
systems.
Did you know about that book before?
I think subconsciously, because I was dating a graphic designer at the time who definitely had it on her bookshelf, but I didn't realize.
Fair enough.
Anyway, so today I want to talk about another book I'm writing called Algebra-Driven Design. And this is sort of addresses the problem, I think, that we are sort of humans are really bad at writing software. And it's sort of amazing that we get as far as we do. So that's sort of the tagline. I'm currently writing a book on this, and this talk is an excerpt of some ideas from that. The book itself is more of a workflow sort of idea, sort of there's case studies, and then there's the philosophy, and then there's the nitty gritty. And it's sort of hard to compress all of that into a 30-minute talk. So this is sort of the more interesting pieces of it. I'm Sandy McGuire. This is my email if you want to get in touch. I have a blog online called reasonablypolymorphic.com if you want to read more about nitty gritty Haskell stuff. I'm on GitHub. And this work is primarily done through Patreon, everything I've learned here. So if you like what you see, and by the end I've sort of convinced you that maybe more is possible, I would love your support on this. So that is my little preamble. Today's slides are available if you want to dive in. And if you don't, we'll talk about it anyway. So that is sort of the gist. Oh, this is not legible. Oh, make this a little smaller. Is that legible?
Yeah, that's good.
Okay, perfect. So I think the biggest problem right now in computer science is that we think too much about algorithms and too much about data structures. If you think about sort of the CS education, there is this emphasis on algorithms and data structures, so much so that there's multiple courses on algorithms and several courses on data structures, right? And I think the implicit message that gets sent by all of this education is that these things are of primary importance, right? That's not to say that they aren't important, but there's an issue here, right? Which is, if you're like me, you probably think in code. And I'd say most software engineers' initial reaction when looking at problems is to pattern match it to algorithms and data structures that they already understand. The idea sort of being most problems in CS are sort of solved, and it's just we need to find the right pieces to combine together in order to express the things that we want. So I think that's a problem. And there's two sub-problems there. One of which is that the first time you look at a problem is you know the least about it that you ever will. And so this tendency to sort of jump to solutions or to implementations, that puts us in a uniquely bad position, because at this point in time, we're going to make the worst possible choice just because we know the least that we ever will. The other problem I see with this is by choosing sort of by focusing on an implementation first, let's say I have some problem and it looks like a graph, right? Usually I'll never go through the work of proving that it's a graph. It just sort of pattern matches as a graph. And if I'm lucky, this thing is a graph. And if I'm unlucky, it's almost a graph. It's close enough that I won't notice that it's not, right? And in doing so, I'm going to sort of blind myself intentionally to all of the structure in my problem that isn't graph-like, right? There might be nuance in the domain that doesn't make sense when viewed as a graph, but it does exist sort of in the domain. And so by immediately jumping to a model, I might lose sort of track of what I'm trying to do. So I think that's the problem. If I can get you to take any one thing away from this talk, it's that we should be less focused on implementations, and we should instead try to put off thinking about implementations as long as possible until we've done a lot of thought on our system. The second part I want to talk about is that we can instead think about our APIs as mathematical objects. And in doing so, we can sort of discover a lot of semantic structure that exists inherently in the problem domain without ever thinking about the implementation. And so if we can find sort of what is the meaning of this thing we're trying to express, that's going to give us a huge amount of sort of power, both for our users and for ourselves, which is the third point here. Sort of going through the work of thinking through what it is we want to build before actually building it, and having a metric for success of have I built the correct thing is valuable really on two fronts. The first is for our users, right? If I'm building a library, I would really like it if it's easy to use and if it solves problems. And I would say that the mark of a good library is not if it solves my problems, but if it solves other people's problems, right? And especially if it solves problems for people who haven't yet been born, or aliens or something, right? If there's a really, really good idea here, it's usable so far outside of the context that I have in mind that it's amazingly useful just sort of in general. And I think that's the mark of a good library. So my claim is that going through this procedure helps us find really good libraries. So that's good for our users, but it also helps us as implementers by going through this work of thinking, what is it that I'm building, and sort of reifying that thought. This sort of comes in the form of mathematical truths about what it is I'm building. And those truths will often inform the implementation and almost always give us the ability to sort of reason about our asymptotics and sort of to derive better asymptotics by just chasing the algebra. So I think that's an amazingly powerful thing, and we will get a chance to look at that. So that's the point of the talk. I hope we'll get through all three of those points. There's some question assumptions here, which I don't think we need to go through. But the last one I think here is actually quite interesting, right? Is that software is a tool for thought. And when we talk about programming languages, the word language there, I think, has a huge amount of staying power. And so if you build a library that's sort of messy, if it requires sort of hoop jumping, and it's not a useful mental model. And I would say the value of being being sort of a computer scientist or an engineer is not in the code that you write, but in the systems that you design. And I think it's sort of too easy to forget that, is that our skill really is understanding systems and much less so about writing code. In doing so, if we can follow all these principles, we can isolate the design of a system from its implementation. And we can put a really, really, really strong abstraction barrier between the two, which prevents any implementation details from ever leaking out because they weren't present when we did the reasoning about the actual the abstraction in the first place. So I think most software gets written this way, right? Someone says, I have an idea for a feature, and then they go and implement it, right? And they never sort of stop to ask, did I implement the right thing? Or is this thing I built, does it solve a problem, right? Or is it just some collection of instructions that were annoying to type out before? In particular, I'd say that the libraries we build should create mental models. They shouldn't just be collections of instructions. They should really give us a new layer on which to reason. And that layer of reason should be completely isolated from the underlying technology, right? There's this law of leaky abstractions, which is that any abstraction is inherently leaky. And I think that isn't true. I think whoever said that is just bad at making abstractions. The crux of this idea comes from a paper called The Next 700 Programming Languages, written by Peter Landon in 1966. It's a really seminal paper. And so he describes a denotational design as something that has these three properties. The first is that each expression is built out of sub-expressions. And this is not so interesting. This one is sort of true of most software, right? But this does suggest that we would like to build objects directly and not sort of with a builder pattern, right? I don't want this mutability idea where I say, build something defaulted and then set X on it and then set Y on it. What I would like to do is say, build some object out of X and Y. The next step is that each sub-expression has some meaning to it. That is to say that there's some sort of mental model that goes into this thing that we're building, and each sub-expression has some meaning. And so later on, we're going to talk about regular expressions. and regular expressions can be built out of other regular expressions. And the question is, what is the meaning of a regular expression, right? My answer is sort of that it's something that consumes strings and then matches strings. But we'll talk about that a little more. The most interesting property that Peter Landon points out is that every expression has a meaning, and the meaning of that expression depends only on the values of its sub-expressions. And the rest of this is that it says it doesn't depend on any other properties of this thing. So that is to say, we can't depend on where this thing exists in the tree. That meaning is irrelevant, right? Is not part of the meaning. The meaning isn't syntactic. The meaning isn't dependent on external variables. The only meaning in this expression that we're building comes from its sub-pieces. And so this has a lot of nice properties, right? What this means is if I understand the pieces in full generality, it means I can compose that understanding to a bigger piece, right? Which is to say that the meaning of the composition is the composition of the meanings. And that is sort of the easiest thing to reason about, I think, because it means if we have local understanding, that local understanding will map to bigger understanding of higher level systems. So a few things are implied by this, right? The first is that every syntactically valid expression is meaningful. And so that means I can't write a program that is syntactically valid but is an error, right? Or doesn't make sense. I'd say this is not true of most software that gets written, right? You sort of need to call functions in the right order. And those things are syntactically valid if you call them out of order, but produce sort of undefined behavior, right? It also means that the meaning of the behavior doesn't change depending on where it is in the tree or how many times it's present. And this sort of suggests that there's no side effects, right? Because I can put this thing in as many times as I want, and it shouldn't be able to, it's not going to do more things the more times I run it. We can compose these programs, and the meanings composed, I think I was harping on this on the last slide. And at the end of the day, what this really means is that there's a separation between describing what we want and then having that thing interact with the world. And then just to contrast this, I'm sure we'll get to some examples very quickly, but just to contrast this, this is not true of most software we write, right? Most software sort of immediately does I/O, and that can't be compositional because it doesn't have the separation between the building and the executing. If we have mutability, that means our values don't depend on our sub-expressions, in which case they are not compositional, right? They depend on something outside of the system. It means that we don't have this mandated order of function calls. So again, we can't call init before we call our other functions. And it means we don't have sort of mutually exclusive options, right? A lot of software says you can turn on flag X, or you can turn on flag Y, but you can't have them both on at the same time. And this breaks our idea that understanding composes, right? Because if I understand flag X and I understand flag Y, if I have the ability to turn on multiple flags at the same time, this thing is syntactically valid to turn them both on. So it sort of turns our problems of what is my software, what is the meaning of my software, it turns it into a data modeling problem, essentially, which means that I can always statically analyze these things. There's no code running, and so I don't have any Gödelian issues. I can always just inspect this tree that I built and say, what is the meaning? Oh, I'll just look at the tree. Because of that, it's always easy to test, right? We've separated the actual running of this thing from the building of it. And so you can imagine if I have some tree that represents a computation, I can run that as an actual computation, or I can just think about it. Or I can write some other way of running it that doesn't perhaps talk to the database or doesn't connect to the internet. In particular, and we're going to get to this in part 3, which is these things are so easy to reason about that computers can do it. And I'd say a huge part of the value of this is once we understand our problem well enough, the computer can do most of the work of implementing it for us. I know that sounds crazy, but I will show you it. So let's stop talking theory and let's do something. So let's build a regular expression engine, right? And the question is, what is the meaning of that? So what do we want to be able to do with a regular expression, right? Given a string, we would like to say, does that string match this regular expression? That's really the only meaningful property of a regular expression. It doesn't really make sense to ask, what's the length of a regex, right? It doesn't, because length is sort of a property of strings. And the string, the regex can be expressed as a string, but it isn't a string, right? So I'm going to say that the meaning of a regex, which I'm suggesting here with this mu, sort of mu suggests meaning. The meaning of a regex is a function from strings to a list of strings. And so this string here is sort of the incoming characters that I want to consume. And the list of strings at the end is all the possible ways of consuming input from this thing that are successful matches of the regex. So you can imagine something like the lazy star operator in a regex, which can match sort of any number of characters but won't go too far. And so I would like to be able to say any possible stopping place along that line is a valid parse of this regex. You can also, something that regexes do that I haven't implemented here is the ability to like pull out pattern matches. I can say, I want to match this thing and then pull it, give it a name. So I can say, pull a link out of this HTML field or something. That doesn't pose any problems here. I just didn't happen to implement it. So for example, actually, this one doesn't really matter. This is just saying sort of I have some meaning of this regex and it's built out of the meanings of the sub-expressions. But this, I think, is jumping ahead of ourselves. So before we talk about implementations, it's sort of valuable to think about this as a data modeling problem, right? And how do we build a regular expression? Sort of what are the building blocks of a regular expression? The simplest thing I can think of is that we can take a character and turn that into a regex that matches that character, right? And so that's just a single character here. I can also match any character, right? And that matches any single character, not the empty character, but this thing is the dot operator when sort of written in regular regex format. I'd like to be able to juxtapose two regexes together, say match this one and then match that one. I'm calling this cat, and this thing is built out of two other regexes, right? This is the thing on the left and then the thing on the right. Does this make sense? Perfect, thanks. I'd like to be able to say I only want to match a regex optionally, right? If it's there, consume it, but if it isn't, then don't worry about it, right? I guess the unstated assumption here is that if any of these fail to match, then we fail to match the entire thing, right? And so that's what optional allows us to observe, is whether or not this thing matches. I might want to branch between two regular expressions, right? I want to say it's either A or it's B, and I can consume either of those things. And finally, I'm going to add the cleaning star here, which is I want to match A 0 times or 1 times or as many times as you can continue consuming it. So I'm going to say these are sort of the fundamental building blocks of a regex, right? And this exists in any regex library that you'll ever see. There's some other things that we might want to do with regexes, but they can all be built out of these terms. And so there's not really, these are syntactic sugar more than they are valuable. There's two other things that happen in regex land, right? We can say, I want to run this regex at the start of a match or at the end of a string, right? And that's the caret and the $ operators here. But these things are non-compositional. I can't put a $ anywhere in a regex because it doesn't mean anything, right? It only matches the end. So I say a $B, does that match anything? Who knows, right? So my claim is that these things are not compositional and therefore they have no space in this thing that we're building. They're useful, absolutely, but because they're meaningless, that usefulness gets in the way. It gets in the way of sort of all the reasoning that we would like to do that we can't because they would exist. This turns out to not actually be a problem, though, because we're going to find better ways of expressing this functionality that is more compositional. So I'm going to say this is our API for regexes, right? But the question is this valuable? To ignore the fact that there are other regex implementations, is this thing complete? Or is there more functionality here that I haven't sought out, right? That I haven't found yet? And my claim is that yes, there is, and we can sort of find operators purely by reasoning mathematically. So we look at the cat operator, right, which is juxtaposition. And we notice that this thing is associative, right? If I have 3 things I want to concatenate together, it doesn't matter where I put my parentheses. I can put them on the left or on the right, which is what this is saying here. And this thing is called a semigroup, which is if I have some operation that is closed, which is to say the arguments are of the same type as the result, and that thing is associative, then that thing is called a semigroup. And a semigroup is sort of this superclass of things, of more interesting objects called monoids. And a monoid, if you see a semigroup, there's almost always a monoid there. And so we should look for a monoid whenever we see a semigroup. And so in this case, a monoid means that I have some regex E that I don't know what it is yet. And I can concatenate that either on the right or on the left of some value, and that doesn't change it ever, right? So if I have some A, I can add E to the end of it, and it doesn't change. It's still equal to A. So the question is there a regex that does this? And the answer is yes. It's an empty match regex, right? This thing always succeeds and doesn't match any characters. So I guess the point is we should add this empty match thing to our algebra because it sort of has a meaning even though we didn't notice it the first time through.
Is that part of regex proper? Is there an empty match?
It's sort of the empty string, right? If you just write a regex, that's the empty string.
Sure.
But you can't really express that thing anywhere else.
I see.
Yeah. So we also have this either idea, right? Which is also associative. So we should also look for a monoid here. And that thing has the fail regex, right? Which is a regex that doesn't match anything. And you might ask, why is this valuable, right? But the answer to that is sort of the same reason that the number 0 is valuable. It's not interesting really of itself, but it's useful as a placeholder. Or if I want to say, I don't have this functionality. And so it's sort of interesting because we can, if we add this explicitly to our algebra, we now have the ability to say, this thing will never match, right? If I show an equality to fail, it means that this thing does not match. So it's not interesting necessarily in its own right, but it deserves to be here because of the monoidalness. And then we can also sort of reason symmetrically. And if I have this either operator, right, the pipe that says choose this one or that one, why don't I also have a both operator, right? It's very rare that you find an either without a both. And so the semantics of this thing are what, right? It should match a string. It's going to have two subrectangles, and it should match them only if both of them match, right? And if they both match, they might match different amounts of characters. And in that case, we make the arbitrary decision that we should use the longer match because it has some better properties. This thing I don't think I've ever seen in a regex library, right? I've never seen this, but I don't see why not. It sort of suggests that you might need to, well, I guess it's associative, right? This thing also has a monoid with the empty match, which is both, and the empty string will always succeed. So this thing probably requires going through the string twice, which is probably slow, right? And I think this is probably why this combinator doesn't exist in any regex library.
Would it not be similar to look ahead?
It might be. It's a good question. Can you expand on that?
So it usually says match a thing and look ahead. If there's something else present, then you got to match. So it sort of vaguely semantically presents itself as both, but right. I don't have the experience reason to justify that.
I think that's a very astute insight. And actually, we're going to come up on that. So good insight. One more thing we'd like to do is, just to finish that thought is, probably this requires going through the string twice, which feels slow, right? And the claim is that we shouldn't not do this just because it feels slow. We should add it because it sounds useful and then figure out ways of making it fast later, right? If you think about this thing as only ever consuming a character once, then you're putting the horse before the buggy. Here's the thing we might want to do, right? We might want to say, oh, I don't want to match a string. And you can sort of express that difficultly in regular regexes, right? I can say don't match any character but H and any character but at E, any character but L, right? But there's no real way of saying I don't want you to match this thing. Some extensions do have the ability to do a negative look ahead, which is what this thing turns out to be. So instead, I want to say I have some regex and I don't want that thing to match. The semantics of this thing, of course, being try to match the regex, and if it does succeed, then I want to fail. And if it fails, then I need to consume something, and my choice is to not consume anything at all, right? So if I'm going to consume the string using my regex, if that thing fails, then I succeed by just giving back the string. I only have a single parse, and I don't consume anything. This thing you can actually compose with itself. If you say negative, negative, that thing is equal to the look ahead that was suggested. So these tools actually give me now the ability to describe this match of like a string that starts with A, right? And so I can say, if I want a regex to only match at the beginning, I can say I want to match both the string itself, or both the regex itself, and also if I put any character before that, I don't want it to match anymore. Does that make sense, right? So that means it has to match at the beginning, because otherwise I could insert a character before it and have this thing still match. Likewise, I can do the last operators completely symmetrically. The only difference is I'm changing where I put the any character. So all of a sudden, I've got these sort of meaningful semantics for this thing that didn't seem meaningful. And so I would suggest we've discovered something here, right? We've found some inherent structure of the problem that wasn't first available, or wasn't first obvious when we were initially talking about our API. So this is all to say we didn't write any code. This was just purely thinking and sort of reasoning symmetrically and saying, this thing looks like that, so what semantics could we have that would sort of flesh out the design? And if we had just dived in thinking, oh, I'm going to just traverse this string, you probably wouldn't have come up with a lot of these things, especially not the both operator, right? So that is sort of the point being, let's figure out what we're building first and then figure out how to implement it, rather than choosing an implementation and then finding things that we can fit into that choice. So that is sort of the slides I have. I'm now going to switch. Do I still have time here, David?
Yeah, I mean, we don't really have a fixed schedule.
Oh,
so
perfect. Okay.
Yeah.
Okay, cool. So I've got I don't know what the button is to clear this thing. The next thing I want to look at is this thing called Quick Spec, which does automated reasoning about programs, which is sort of amazing. And so here I have a small implementation of this regex thing I've been talking about. Some of the names are not the same, for which I apologize. But my implementation is really, really stupid. I have this data type called regex, and then I actually implemented this thing as a data modeling problem. So every operator, my cat operator, is implemented as a data type. It's just a sum type that says, I'm a cat, right? I don't know what's on the left. I don't know what's on the right. I don't have any semantics. I'm purely syntactic. And then the cat operator just says, I'm going to build myself out of this data type. I also wrote a little law here that does right association. And so I can actually pattern match on this thing, but that's not particularly interesting. The point really being is that I wrote the dumbest possible implementation, which is this thing is purely a sort of a syntax tree of the regex I want. And then I wrote a little function that consumes these things. And so what it does is it pattern matches on each of those constructors, and then just sort of calls itself, this thing is exactly the denotational semantics I chose earlier, saying I have a list of strings, or I have a list of characters, and then I'm going to produce a list of strings, and those are all the possible parses. So for example, if I want to fail, then I just always return the empty list. I never can match anything with the fail constructor, compared with the cat, in which case I can consume one and then consume the other. So the point is, like, I didn't do any thinking about this implementation. This is not a fast implementation by any means. But the point is more, it's important to really nail that this thing does what I think it does. I haven't done anything clever here. And so because there's nothing clever, it's really hard to sort of have got the wrong implementation. So to talk now, I want to talk about this thing called Quick Spec. And so the idea is I can expose these functions to Quick Spec in this signature I got here. And so this is sort of all the functions I want Quick Spec to care about. And so I just say, okay, I have some constructor called cat, and the implementation of that thing is cat. And the idea is that Quick Spec is going to generate every possible syntactic term of my program and then compare them using the implementation I gave to say, are these things the same? And the question is, what does it mean for two things to be the same, right? We said it's not syntactic. What it is it's this idea of what value do these things have? And so I say two things have the same value if they consume the same string and they produce the same values, or they produce the same chunk of a string. So without further ado, let's run this thing. And so I'm going to run my program, and QuickSpec goes and it generates a bunch of laws that are true, which is to say, if you write this regex or that regex on either side of the equal sign, they will match exactly the same strings. And it's like, it's doing a huge amount of work here, right? So if I scroll up, we'll say, actually, you know what? We'll get rid of some of these. Yes, you're one of these. Again. And we don't have to run too much, but you'll see it's coming up with things, right? It says if I concatenate anything to the empty string, then that's the same as just having that thing itself, right? So this means I can eliminate a cat with the empty string, and this thing is that monoid law that we saw originally. It says that if I have a star with a star in it, that's the same as only have a single star, right? And because star has sort of bad asymptotics where it needs to sort of do potential look ahead, this is potentially an actual good optimization, right? If I know this thing is true of my implementation, then that gives me a chance to optimize away that case. Can we just let this thing match? I think it comes up with like 50 laws or something. Every one of these. Sorry?
Are these laws like proven by this quick?
Yeah, absolutely. That's a good question. So yes, they are.
So it's not even statistical laws. It's like.
So sorry, yeah. So these things are statistical. And so what I've done is I wrote a little piece of code that will generate a random regex. And so what it's doing is going to generate these two terms and then try to prove them unequal. And so what it does is it runs 10,000 tests of randomly generated regexes and randomly generated strings and says, for each one of those, do these things line up? That's not to say this is a real proof, right? But if it works for 10,000, probably it's true, or it means you have a bug in not your implementation, but in sort of the code that's generating random values.
Is it selection entirely random, or is it sort of guided through the search space somehow?
Is the selection of random regexes?
Yeah.
Guided? It is. So I actually just wrote this code myself, and so I said
I see.
these three constructors are cheap to generate, and then things like star are sort of expensive because they can loop for a long time, and so I sort of manually annotated this. So there was a little bit of instrumentation on this, but it's linear in the amount of constructions I had, and mostly it's just sort of threading the code into the right place. This is more a quirk of Haskell, I think, than anything else, because the type system makes this a bit annoying. So the point I'm trying to make is twinfold, right? Each one of these laws is true of my implementation. And if my claim is that the implementation is so stupid that it's correct, that means these laws should be true of any regex implementation, right? And what that means is that I can turn these things into regression tests. When I can sort of re-implement my thing using all the clever things I know about regexes, right? I can say, I want to do some sort of clever matching where if I know that this subpattern doesn't exist, I should skip ahead. Performance enhancements that are hard to, make improvement in my speed, but are sort of tricky to get right. So if I add this thing called with print style for quick check to it, what I find instead now when I run it is that, this thing will actually generate test cases for me. I don't know if you're familiar with property tests, but the idea is I can write two expressions that should be equal for any parameters, right? And so I say, for any x and any y, this expression should be true. And then the property test will use the same random generators I used, and it will try to prove these things. So the idea is I can write a dumb implementation get the computer to generate these regression tests that prove my semantics for any implementation must be equivalent to the model, this like dumb implementation I wrote, and then I can go and produce a better implementation, right? One that's faster. So the first thing is it's nice to have these regression tests. It tells me immediately if I've got a bug anywhere in my semantics, because every single one of those needs to be true. And if you look at this, I think I'm producing like 100 tests here, and each one of these is a property test, which can generate arbitrarily many unit tests. And so the last time I did this, I think I got 10,000 unit tests for free, which is a good amount of work to not need to do myself. The other thing I get from this is sort of it gives me an idea of what would an implementation look like, right? So I mentioned earlier that is that this both thing might be slow, right? It probably needs to traverse the character twice. And so the question is there something true in my semantics that means I can lessen the amount of work that is necessary there? And I sort of already know the answer, so I'm just going to do a little bit of work here. So what I can do is run this again, and I can sort of change the functions I'm interested in. In this case, I'm only interested in laws that involve the both combinator. And so it's going to run for a little bit, and it's going to tell me all the laws that are true of only both. And sort of any laws that are implied by the rest of it will get canceled out. So there's this law number 12 is kind of interesting, right? It says if x is not equal to y, then if I ask for both character x and character y at the same time, then that thing must fail, right? That thing is sort of obviously true when you think about it. I think there's interest here, right? Which is to say this is a conditional law. This isn't always true. It's only true if x is not equal to y. And in the case that x is equal to y, as in law 14 here, right? If I'm concatenating something on both sides of the both, it means I can pull that out, right? And so the both sort of distributes through this. And so if I have a common prefix on both things I'm trying to match, I can pull that out. And right, like this is an implementation idea, this one right here. Because between law 12 and law 14, I say, oh, if I ever see this, then I can immediately fail. And if I ever see this, then I can pull out that logic and reduce the amount of work I need to do inside of both. And sort of when you run these things back and forth, when I construct my original regex, if the constructors for that thing are sort of doing these checks, then what I can do is immediately eliminate all this work that might need to happen otherwise at runtime. So I think that is my talk. The high level idea is that I think we're writing software badly if we spend a lot more time thinking about what we're building and having the meaning of what it is we're building in mind. Then we can use cool tools like this, which do a huge amount of the implementation work for us and sort of the reasoning and the clever thinking and at least the testing for us. So thank you. And if you have any questions, I'd love to answer them.
Sweet, thanks, Andy. So these laws that pop up, it almost seems like they could be optimizations that you just inline into your I guess compiler or
Absolutely
directly.
Yeah. That's a good. Yeah. Sorry.
Could you do that automatically? Just
you could. The problem is a lot of these are not valuable. So you absolutely could. I think it requires some thought. So for example, like line 6, this thing doesn't terminate if you always do it, right? I just swap my arguments back and forth. And I'm not sure you could statically determine if these things will ever terminate. So I think there is sort of some thinking that needs to happen. But yes, absolutely, you can implement these things. And if you look actually at my implementation, a lot of these things I implemented sort of exactly that, thinking, oh, I don't want to do this myself because I know this thing is true. And it will make my tests faster if I include this sort of special case optimization. Does that answer your question?
Yeah, it does. It does. I'm still thinking about how to do it automatically. You know, this seems like it'll just optimize itself if you do
Right.
it. If you could imagine, you take one of these laws and you add it to your interpreter, and then you time the execution of your next run and see if it improves things.
That's
and if
cool.
it did, keep it. If it doesn't, try the next one. Let it run overnight. You get back in a.
I think there is a subtlety as well here, though, which is that just because this is my public API, these functions, that doesn't mean my implementation needs to necessarily do this pattern matching thing, right? And a lot of the ideas from this talk came from a paper called The Design of a Pretty Printing Library by John Hughes, which I super duper strongly recommend. And in that, he looks at sort of the same idea. He wants to build a pretty printer, and he thinks about, he builds a model exactly like this, and then says, oh, I have this function that would be easy to optimize if it only looked at canonical terms of this form. And so he sort of runs this backwards then. He says, assuming this is my canonical form, can I express all the other things in terms of that? And so there's sort of the bidirectionality. So I think you might find local optima if you just optimize this implementation without sort of stepping back and asking, is this what it should look like in the first place?
Did that paper end with like 5 pages of template Haskell?
I don't think so.
Am I thinking of the right one? Okay, maybe not.
I did just post it to the Slack, and it ends in 3 pages.
3
of
pages.
Only 30. Yeah, the what was sort of a guiding principle behind this quick spec library was how can you sort of automate a lot of that paper away? And it finds all of the laws that he found by hand and a couple more that he missed, which I think is really interesting.
Yeah.
So
He was also the one who wrote QuickCheck, if I remember correctly.
He was. Brilliant man.
Yeah, cool.
Cool. Okay, I think I need to run, but thank you all so much. Again, if you're interested in more on this, I'm writing a book, and you can find it on Patreon at the slides originally. So
Nice.
Thank you all. Hope you have a great day, and enjoy it.
Yeah, thanks, Eddie.
Thanks, Andy.
Thank you. Yeah.
Thanks.
Sorry I was late.
Thank you.
What I caught was great. Thanks.
It's recorded, so all the best, guys.
That's pretty cool.
Mm-hmm.
Yeah, the quick spec thing was impressive. My mind also immediately went to how can we have this automatically optimize our code?
Yeah, I feel like we were all thinking the same thing. Like as soon as I saw like that output, I'm like, oh, you could just like generate like compiler optimization passes automatically. And yeah, if you like hook it up to like some sort of optimizer, some sort of like optimization framework that is optimizing for, like, it doesn't even have to like run it. It could just be like if it has an idea of like cycles per like instruction, if you're like generating assembly code or something, like even just something like that, you can find like clever